Okay, so we all have study guides done, right? Yes, perfect. Okay, so I already had an email talking about a student told me that he's struggling with two particular problems, so we'll go over that for the sake of, for y'all and for the video, because I mean they're pretty interesting problems, so I think they're definitely something that's worth hammering down. But I guess to start off, what problems did y'all have on the study guide that y'all maybe need more more practice on, or maybe just want me to go over it, et cetera, et cetera? Just give me some numbers.
12 and 20.
So yeah, 12 and 20, yeah, those are the two that I mentioned for sure. So 12 and 20, what else? 8? So I'm just going to write them. 12, 20, what else? Any other problems besides those three that y'all aren't too confident on?
Can you re-go over like the rules for sig figs?
Yeah, I can go over sig fig once again, yeah. So just sig figs. Anything else?
Can we like go over like the you know how you fill in the chart with the isotopes and ions?
Oh yeah, the element chart, yeah. So I think that's problem 24. Are you referring to the element chart, or are you referring to the average atomic mass calculations? Or both?
Both.
Both. Okay. So.
I just want to make sure I did it right.
Yeah, of course. Yeah, no, and I 100% get that. Like, this is just, if you're not 100% confident on some of these, we're just going to kind of go over them. Any other? No? So y'all felt pretty confident in, like, the definitions of the words, and y'all understood, like, a difference between atomic number, mass number, average atomic mass. Yeah, Taylor?
So like I remember 11 with like the sulfur one.
Yeah.
I think I wasn't sure on that one. So.
As the
I
atom
don't know what my
sulfur.
specific issue was, but I just knew I started it. So.
Okay. So I'll make sure that's on there as well. There we go. Any other ones? No? All come to mind? No? Okay, so let's go over sig figs first. So, the main problem I'm assuming y'all are going to have with sig figs is where the zeros work, how the zeros work. So I'm going to skip over the fact that we know that a non-zero number is significant, right? We know that. That's pretty obvious if it's a number that's not zero, it's there. So let's go through the three types of zeros. So first we have leading zeros, right? So that's if we're either something like this, or more commonly, something like this. Now, are leading zeros ever significant? Yes or no?
No.
No, right? So, again, these, pretty obvious to see. These are pointless, right? 100, absolutely pointless. These a little bit harder because there's the decimal place. But remember, in the same way that if I say I got 100 likes on Instagram, I didn't really get 100 likes. I have around that much. I'm using those zeros as a placeholder to show how big the number is. In the same sense, leading zeros when there's a decimal place are placeholders to show how small it is, right? Like, let's see, think of a good example. Like, it's hard to think of a real life example for this, right? Because, like, I mean, I guess you could say something like, maybe you're just like that guy has a 0.00001% chance of ever beating me in said sport or basketball or whatever, you know. Bad example, but it can kind of reach for that. That technically, if we're going by stats, you know, probably necessarily maybe is not 0.0000001, but those zeros are used as a placeholder to show how small of a chance that person has, right? So in the same sense, it's just kind of measuring that. So that's why our leading zeros on either case, never ever significant. That makes sense? So yeah, first one's pretty good. That rule's pretty easy to understand. It's just hard to keep track of sometimes. Yeah.
I have a question. So what if if numbers like 0.1, is that 0 still not significant?
Like, are you talking about 0.1? Like that?
Yeah, or like a 0.59, something like that.
Yeah, no, that zero is still not significant. It's a leading zero, right? Because again, the real numbers for this start at this this significant digit right here, even when it's like smaller. So those are just kind of there as a placeholder, so you're not just writing like 0.1 or 0.59, because sometimes it can be a little sloppy and maybe a little confusing sometimes to write that. So that's why you see it a lot of times in books, they have that 0 placeholder there, just to make the number look nicer. Yeah?
Oh, for the, like when you're doing conversions like grams to moles or whatever, or grams to atoms, do you take the sig fig from like the entire problem, or just like whatever like the last problem you do?
So I mean, you want to take it from the number that you're actually dealing with. So, and I guess the confusing thing would be like, well, we're using Avogadro's number, but when we do grams per mole, we have like 6.02 particles over 1 mole. So remember, like the number itself and the conversion factor itself is still 6.02 particles per mole. It's just that you can divide this by 1 and you still got 6.02, right? So this isn't really, this is more of an exact number because it's a ratio here. But this is the number that you really need to worry about sig figs. So like if you did like the 6.02 atoms over 1 mole. It's not that your final answer is going to have 1 sig fig, because 1, that would be ridiculous. And 2, it's because, again, this is kind of just there to help out with the ratio. You're really, the reason this is here so you can cancel out the units and get to the units you want to, right? And so this number itself is exact because it's not Avogadro's number, and again, just reiterate this, it's not just 6.02. So yeah, this number itself is an exact number, so what we know about sig figs is exact numbers are infinite, right? So you can think of this as an exact number, not just a 1, because again, it's not really a part of the whole ratio here. It's the same thing with like when we're using our molar mass, right? If you have like calcium, which is 40.08 grams per mole, and you have to like divide by 1 mole, right? It's the same deal there. That 1 mole is exact because that's just the conversion factor. It's not that we're adding a 1 to the equation or anything like that. So that digit, that number is exact, which means that it has infinite. So we don't really worry about that. Does that make sense?
Mm-hmm.
Yeah. Okay. Yeah, it just depends. Like, you're really worrying about the number that you're actually dealing with, and just putting the 1 there doesn't really change anything. So you shouldn't be trying to focus sig figs on that 1 there. Other rules of sig figs, right? Second rule for zeros. Zeros that are captured. So let's say we've got 106 here, 0.0107 here. Are these zeros significant? I see a yes, I see a yes. Yeah, exactly. These are significant. Anytime a 0 is captured, it is always significant. Because it's kind of important to show the rest of the number with that 0 in place. So that one's pretty easy to remember too. If it's in between 2 numbers that are significant, then the 0 is significant. The last one's the tricky one. Is we've got 2 different examples of trailing zeros. Now, are these zeros significant? No. See, you're nodding head yes a little bit, but I think, okay, no, right, because there's no decimal place here. Again, like I was saying earlier, these are used as placeholders. Are these zeros significant? Yes, exactly, right, because of that decimal place. We're showing, we need this decimal place in order to show the exact number. Again, it's kind of like if we were measuring this in real life. Let's say this was milliliters and we had a graduated cylinder that measured to 1/10 of a milliliter. We would have to include that hundredths place, right? Because for that certain uncertainty digit, even though we're pretty sure it's exactly 15, you never know, and that's what the uncertainty digit is for. So it's still counted as significant in that case. All right, does that make sense for zeros? Yeah. So yeah, the really only confusing rule is that trailing zeros count as significant only when there's a decimal place. Otherwise, they're not. Captured zeros are always significant. Leading zeros are never significant. Does that make sense?
What about 15.100?
15.100. Well, what did I say about trailing zeros? What's the rule? What makes them? When are trailing zeros significant? when there's a decimal place. So it could be even even if it's like that. These zeros are all significant. It's just because of the existence of this decimal point, you're now showing that you're basically going after this number again. If we were measuring this is milliliters again. Let's say our graduated cylinder went by like milliliter increments, right? So we can measure out to the zeros place, or not the zeros place, the ones place, and then we have our certainty digit at the tenths place. So we can still measure that there, and that's why that decimal place is so important to cover those significant figures in that case. So yeah, anytime there's a decimal place, trillion zeros are significant. If there's no decimal place, trillion zeros are not significant. Which I know is a little confusing, it's a little weird, because again, this has one sig fig, this has 3 sig figs. It's really dumb, I get it, but that's just how we deal with significant figures. And it's because of that decimal point. That makes sense for sig figs?
What about like the rules of addition or subtraction?
Yes. So for addition and subtraction, you're looking for the least accurate measure. So when I say least accurate measure, what do I mean by that?
Least amount of sig figs.
Not necessarily the least amount of sig figs.
Oh, the one with the lowest, like.
So let's write out 2 numbers here. 1,500 and 600. 679, right? And let's say theoretically it's something like this, right?
Yeah.
Or something like this, right? So what if we did just adding this? How should we add this together? Like where should we round it off?
Run off at the hundreds.
Round it off at the hundreds, right? Why?
Because 1,500 is at least less accurate than 679.
Yeah, 1,500 is less accurate at 679, right? Because our last significant digit in 1,500, right here, this 5, right? And then our last significant digit at 679 is at this 9's place here. So this is accurate to the 10th place, or accurate to the 1's place. This is accurate to the 100th place. So when we do the math here, we do it to the 100th. So 9, 7, 1, 2, so round this off to be 2,200, right?
Wait, you lost me there.
I just did the math. So that's just adding these 2 together. I got 2179, but because we know that we have to round to our 100th place, because this is the least accurate of the 2, I rounded it to 2,200.
So how is it the least accurate again? Like how does the bigger number like it?
You're basically measuring what the last significant digit is in your number, right? So the last significant digit here is this 5, because again we have trailing zeros, but there's no decimal point. So these zeros aren't important to the whole number.
Oh, okay.
And so this is here, they're just there to show size. And like I said, additionally here, those 2 zeros at the end here are there to show size now, right? Because we technically had this much, but we can say it's about 2,200. Technically our measure is this, but because we're doing our rounding for significant figures, we're going to say it's about 2,200.
Okay, I get it.
Yeah. And so the same would be if, let's say we had decimal places and such, so like if we had like a 4.79 and then a 0.000 or 00. Well, this is a stupid problem, but still. Let's say we're adding these together, right? So how accurate is this number to?
The hundreds.
Hundreds place, right? What about this number?
Thousands.
Thousands.
Yeah, thousands place, right? So if we do our final answer, what should we round it to?
Hundreds.
Hundreds place, exactly. So that would be 4.795, which if you round it to the hundredths place, it's still going to be 4.80. Because remember, again, that decimal place, this is still significant here. Does that make sense on adding and subtracting? Yeah, and then with multiplication and division, which is what you're going to do most of your problems with, especially in this chapter, it's always just least number of sig figs, right? So if you've got 2 sig figs, you've got 4 sig figs, you're multiplying those numbers together, how many sig figs should your final answer be?
2.
2, exactly. Yeah, so multiplication and division, pretty simple. Addition, subtraction, you have to think a little bit. But those are kind of just the rules. The rules are different, and it's important to remember the difference. It's not just least sig figs for each. Though generally it does kind of work out that way, but sometimes it doesn't. So it's important to remember you're going to the least accurate measure here. And that's what sig figs are measuring, is the accuracy, how accurate your measurement goes out to. Alright? Does that make sense for sig figs? Any other rules that you think I need to cover for sig figs here? Or you all kind of understand the idea? Yeah? Okay. So let's go into our problems then. So we start off with number 8, and Mr. Hobbs, I wish I had a printed copy, but I don't think, we didn't print out one, but I do have, oh, I didn't type in the right password. That's okay, I can put that there. So let's start with number 8 here. What are isotopes? How are they the same? How are they different? So let's start with what are isotopes. Who can tell me what isotopes are?
Atoms of the same element that have different mass numbers.
Gotcha. Why did I erase that? Well, I meant to make it less confusing. Okay. I'm going to make sure right now I remember what I have. So I just want to keep this off camera so it's not confusing which problem we're working on. There you go. Those are the numbers we had. So 8. So what did you say an isotope was?
Atoms of the same element that have different mass numbers.
So particularly with the mass numbers, because they have different mass numbers, what does that mean about the elements? They have a different number of what?
Neutrons.
Neutrons. I heard neutrons.
Neutrons.
Do we all agree on neutrons?
Yes.
Okay, cool. And I know you slipped on protons a little bit, but remember, neutrons are not charged, and that's what we do when we have an isotope. We have neutrons. So the exact definition, particularly, is atoms of the same element, which again, if we're talking about atoms of the same element, what does that mean? Like what, if it's the same element, what particle does that element share that wouldn't change? Protons, right? Oxygen is always oxygen because oxygen has 8 protons, right? Mm-hmm. Exactly. So again, remembering that same number of protons. I'm just going to put plus here because I'm lazy and I don't want to write out protons. But y'all get it. With different mass number, and again, this is representing different number of neutrons. Can't really use a symbol for that, but... Right? Okay, so the next part. If we're talking about the same between each isotope, so what's the same between isotopes?
Protons and electrons.
Protons and electrons, okay. Alright, so protons and electrons are the same. And then there's one other thing that's the same between different isotopes of the same element. What do y'all think? Is oxygen still oxygen if we have 16 protons and 17 protons? Or sorry, if we have a mass number of 16 versus a mass number of 17, is oxygen still oxygen? Right, okay. So does that make sense that maybe oxygen would have the same properties of oxygen between the two? Gotcha. So yeah, that's the third distinction. Remember, oxygen is still going to be oxygen between the two. So it's going to have the same properties. Or same chemical properties, rather. Yeah, chemical properties. The only difference is that some isotopes are stable, some are not, and so that will lead to sometimes radiation, and so technically that would be different, but it's, again, oxygen is still oxygen. All right, now what's different? right? Different number of neutrons. All right, and then there's one other difference. If they have the different number of neutrons between elements, what does that also mean about the different elements? Like, what else would be different between them?
Their mass number? Their mass number?
Their mass number, right? So also we can also consider their atomic mass might be different, right? Like if their mass number is different, again, we're adding one neutron. Does the neutron weigh enough to make a difference inside the nucleus? It does, right? I saw a head nod, so I'm assuming that meant yes, right? So it does make a difference. So you're going to have an isotope of, it's like, if we go to carbon 12, right? So carbon 12 is, AMU is like 12, right? Carbon 14, AMU is like 14 point something. I don't know the exact number, but they're going to have different atomic masses as well. So that's something important to remember. And that's the case because, I mean, we wouldn't be able to find the average atomic mass if they didn't have the different masses, right? Because if they all have the same mass, we wouldn't even have to worry about average atomic mass. But since they're different masses, we've got to make sure that we take the atomic average mass, and that's what we end up putting on the periodic table. So, does that make sense? Any questions on 8? Nope. All right. So let's move on to number 11. Okay, number 11, we have an atom of sulfur has 16 protons, 18 neutrons, and 18 electrons. And so we'll start with what's in its atomic number. So let's look at that for a second here. So we have an atom of sulfur with 16 protons, 18 neutrons, and 18 electrons. So, first off, atomic number. What is sulfur's atomic number? 16. Why is it 16?
Because it has 16 protons.
Exactly, yeah. Sulfur is always sulfur because it always has 16 protons, remember. So yeah, atomic number? Always 16 for sulfur. Second number, what is its mass number?
34.
34. Now how did you get to 34, Cooper?
Protons and neutrons added together.
Protons plus neutrons, right? Everybody agree with that? Alright, awesome. So, let's talk about the charge of the atom. What is this atom's charge?
2 minus.
-2.
Okay, so I heard 2 minus, I heard just negative. Any other thoughts on that? So, Madison, why did you say it's 2 minus?
Well, I looked at a little PowerPoint thingy, and there was a 2 minus in the top left corner, top right corner, and it said that was charged. So
Okay, but why is it 2 minus? Let's take a look at our protons, neutrons, and electrons here.
There's 2 more electrons than protons.
There's 2 more electrons than protons, right? Remember, protons, positive charge, electrons, negative charge, and they kind of cancel each other out in a sense as why those atoms are neutral, right? But we've got 2 extra electrons here. So you're right in the sense that the PowerPoint would have this written as like sulfur 2, or should be 2 minus, but didn't see that. That it'd be written out like that, right? And that makes sense because again, what we're talking about here, we've got 16 positive charges and 18 negative charges, so our net charge here is going to be -2. Yeah.
Okay, so like on the chart it has like an isotope and it also has an ion. Is that like normal, or is that me like I don't know what I was looking. So like it has like 128 TE and then the charge is
Are you talking about
2 negative.
which chart are you talking about?
The chart on the second guy.
Oh yeah, so you're talking about the T. I think it's selenium. I think is what T is.
So is it supposed to have like, different number of neutrons and electrons for that?
I mean, let's think about it, right? So if you're trying to find selenium, and I don't know exactly if that's the most abundant isotope of selenium or if that's the only isotope of selenium. It probably isn't, given that selenium is a pretty big element. It has 52 protons, so more than likely it's not the only isotope. But yeah, so again, remember, when we're talking about mass number, what is that?
A number of protons plus neutrons.
Mass number is protons and what?
Plus neutrons.
Yeah, mass number is protons plus neutrons, right? So technically, selenium-128 would be an isotope, right? But that doesn't necessarily mean that it could also be an ion too, right? Because they're kind of independent of each other in a sense, right? Because if we change the protons, we get a different element, right? If we change the neutrons, we get what?
Different mass.
Which gives us different whats? Same element with two different isotopes, right? And so if we change the electrons, we get two different what?
Charges.
Charges, but what's the name of that particle that we're talking about?
Ions.
Ions, right? So you can have something that's an isotope of a different element and an ion too. An isotope is necessarily like, even the most common isotope of an element that you'd see in nature is still an isotope, right? Carbon-12 is way more abundant than carbon-14, right? But carbon-12 is still an isotope of carbon. It's just that we see that isotope way more often. So it doesn't change that the element's an isotope just because it has a different, just because it's the one you most commonly see. It's not like there's like a base model of the element and then everything else is an isotope. Everything is an isotope. Unless you're talking about like beryllium, in which case it's only one stable isotope, which we'd still call it an isotope. It's just that you don't ever see anything else. Unless it's man-made. You could theoretically make it. But that's a whole other topic, and that's for somebody to have a much larger degree than I do to try to make their own elements there and known isotopes. But I guess the question you're trying to ask is, I think I've tried answering that question where like if you can have a different number of neutrons and ions. Oh, the other question I think you probably have is like, okay, so why was it not 52 neutrons? Is that what you're trying to say? And we'll go over that in a bit. But I guess the reason, we'll go over this in radioactivity, why it wasn't 52 neutrons as like the standard.
I was 76.
Yeah, it is 76, right? But I was trying to figure out what you were asking me.
You answered it because I was confused. Like it can be an isotope and an ion. I thought it can be.
Gotcha. Yeah, and technically that's probably the most that's probably the most abundant form of selenium there. I could be wrong, and we'll get into radioactivity. But elements like to exist in a proton-neutron ratio in order to be stable. The bigger the element, the bigger that ratio normally. So, and it's not always the case. Some elements are always going to be an exception. But like normally with the bigger elements like selenium, they like to exist in like about a 1.5 neutrons to like one for every proton. And so that's why it's not just like the normal isotope. Like that's why the most abundant form is not just with 52 neutrons and 52 protons, if that makes any sense. So we'll get into that more in the next chapter. But let's go ahead and start blitzing through these so we can make sure to get through all these questions. They don't want to necessarily spend too much time on one and then skip out on the rest. So if it's a -2, is this an anion or cation? Anion. Awesome. All right. And then, so has it undergone reduction or oxidation? I briefly talked about this in the last video. But has it undergone reduction or oxidation? Reduction, right? Why is it reduction?
It says because it gains electrons.
Because it gains electrons, right. So if you didn't see the video, we have this nice little acronym called oil rig, which is oxidation is loss, reduction is gain. Reduction is gain in electrons, oxidation is the loss in electrons. And that's because generally, like, oxygen is really hungry for electrons, so if something gets oxidized, it loses electrons. And then somebody had a good idea of saying, oh, what if it gains electrons? We'll call it reduction for gaining electrons. Honestly, a bad idea in foresight, but it did give us this nice acronym. So, you win some battles, you lose some battles. All right? Does that make sense on 11? Awesome. Let's move on to 12 here. This is kind of more of the calculation steps. So, go ahead and move on to number 12. What is the mass of one atom of argon, right? So if we're talking about just the mass of argon, what is the mass of argon?
39.948.
39.948. What are the units on that?
Grams a mole?
So that's what we're useful for conversion factors, but if we're just talking about...
Just grams.
Not just grams. There's a unit for elements.
Oh.
Y'all remember it?
Particles?
And I heard AMU.
Particles?
That's just like the number of particles. We're talking about the weight, or like the mass. You?
You?
I heard AMU. So yeah, it's going to be AMUs or atomic mass units. But again, it's kind of misleading because again, 1 AMU is equal to 1 gram per mole. So that's what they're interchangeable in the periodic table. But if we're talking about specifically the mass of just this atom here, we're talking about just AMUs. If we're talking about the molar mass of something, we're talking about grams per mole. A little confusing. We use different terms for different things, but they're relatively the same. And the reason that is because 1 AMU is like something 10 to the negative 24th grams. And so just use AMUs to be easier. But again, that conversion works out nicely for 1 AMU to be 1 gram per mole. So it just depends if we're talking about the mass of just one atom or if we're talking about molar mass and we're trying to convert between cells. What is the mass of 1 mole of argon atoms? So this kind of goes into the next part. Mass of 1 mole of argon atoms.
I tried to look it up, but I'm so confused.
All right, so let's walk this through. So again, I just said it, but 1 AMU is equal to what?
1 gram per mole.
1 gram per mole. So we can convert this directly, right? So this is 39.948
Grams a mole.
grams per mole. So if we had 1 mole of this substance, how many grams do you think we have?
39.948.
Exactly.
I wrote that down,
I did the
but I was not
conversion.
understanding why that was the answer.
Yeah, and that's because, again, that's the tricky... So if we're talking about why that's the answer, so we can just do it conversion-wise. Because remember, this ratio is saying that we have 39.948 grams of argon per every mole. So again, this is talking about a ratio, remember? So if we're going to do the actual conversions for it, again, let's set up a little table here. We have 1 mole of argon, right? And we're trying to get the grams, right? So if we put this conversion rate on top, we have this ratio of grams per mole, right? So it's just like the dimensional analysis problem. We can cancel out these moles. And again, these are moles of argon, and you can cancel them out. I just don't usually write the argon, but if you're dealing with multiple elements, it might be helpful just so you can keep track of it. So yeah, we cancel out moles of argon, and we're left with grams of argon. And so that's how the conversion would look like if we wrote it out all the way. But also, this is 39.948 grams per 1 mole, because it's a ratio, right? So you can literally just see that and be like, oh, okay, so 1 mole is going to have that many grams. Does that make sense? Both the short way and the long way? All right, perfect. So yeah, that's kind of like an introductory problem to this dimensional analysis. And then 20 is going to be kind of furthering that. So 20 here. Let's go down here. How many grams of gold contain the same number of atoms as 107.87 grams of silver? Okay. Did anybody have a guess for this? Did anybody was able to work this out, or were y'all all confused?
I didn't even try.
Didn't even try?
No.
I read it like 5 times. and I was like,
It's very confusing, yes. So we'll walk through this one step at a time. So let's talk about what we were given first. So we were given, what number were we given in the problem?
Silver.
107.87 grams of silver. So let's start with that, right? Silver is Ag, I think.
Yes.
Okay. I couldn't remember what's on my head. So I have this, okay? So we're trying to get the grams of gold that contain the same number of atoms as grams of silver. So if we're trying to compare the two, it's probably easier to go if we know, right? So I know our conversions to get, can we convert these grams of silver into atoms of silver?
Yes.
You think so? All right, so how do we do that?
Go to
Go to moles.
Okay, how do we go to moles from grams of silver?
The mass, right?
The
periodic table.
periodic table, and you're using what? The
Mass.
molar mass?
mass.
Yeah, there you go, molar mass, right? So, you're right, just use the right terms, because it would be confusing if you see that on a test and you have no clue what molar mass is, right? Just making sure to keep that in mind. Use it constantly so it stays fresh in your brain, all right? So, molar mass of silver. Who can tell me molar mass of silver? Just give it a little look-see.
Whoa.
Yeah, it's kind of hard to tell. Let's just...
107.8682.
8682. So, the one that he gave on the test is actually just 107.87. Or the answer guide. So we'll use that. We'll use 107.87, but yeah, in the future, depending on what, it depends on the periodic table that somebody gives you. Sometimes they're different, which is weird. It just depends on how people calculate it. So, the one that he had when he did this was 107.87. So again, we have, I already put this on the bottom, so I spoiled it, but right, we needed to cancel out the grams, right? So we need to put this on the bottom, right? So then on the top, what do we put?
1 mole.
1 mole. Yeah, 107.87 grams for 1 mole, okay? Can we do this mental math in our head? How many moles are we going to get of silver?
1.
1. All right. So 1 mole of silver right now. So we have 1 mole of Ag here. So we could convert to atoms all the way, right?
Yeah.
But does 1 mole of silver? So is 1 mole of silver the same number of particles as 1 mole of gold?
Yes.
I heard both. No,
Wow.
Camp. Why do you think no?
Because they're, I feel
Two
like
different masses.
The 2 different masses?
Small masses.
Okay, and then yes, Camp. Why do you think yes?
Because 1 mole. I don't think yes.
Oh,
Because there's always going to be the same amount of particles. It just depends on how dense they are.
So yeah. So you're saying that 1 mole is always 6.02 times 10 to the 23rd, right?
Oh, that's a mesh.
Yeah. So 1 mole is always 6.02 to the 10 to the 23rd. It never changes. Like again, it's the dozen. Just because you have a dozen feathers versus a dozen bars of steel doesn't mean that you don't have 12 of both, right? It's just that one is way heavier than the other. So we can't convert to atoms here, but what we could do is now that we understand that this is a mole, we can convert directly to moles of gold, right? Because if 1 mole of silver is always going to equal 1 mole of gold, because it's the same number of particles. So we still have 6.02 times 10 to the 23rd. We just convert it back to gold. So again, these cancel out. We're left with our 1 mole of gold. And now, the question asks us to find how many grams of gold contain the same number of atoms as 107.87 grams of silver. So how do we get from moles of gold to grams of gold?
Go back.
Go back to the periodic table, all right? So what's our molar mass for gold?
196.96655.
That's a lot of numbers. So I'm going to use what he put down here. So 196.97. Again, you'll have a periodic table that you'll be able to use on your test so that you can see which numbers to use. But so if I have 196.97 grams per mole, how am I putting this down? Like, do I need that number to be on the top or on the bottom here?
Top.
Top?
Because grams shouldn't be canceled out. Mole need to be canceled out.
Right, we're trying to cancel out moles. So we need grams. So 197.97 grams per mole of gold. So again, cancel this out, and we're left with 197.97 grams of gold. And we have solved our problem. Does that make sense? So I think the recipes are similar, but they're not as easy as the first one. Because the first one is technically easy because it's like we're dealing with the same number of grams as is the molar mass, but these are going to be a little bit different. So let's start with the second one here. So number 2, so how many grams of sulfur contain the same number of atoms as 8.0 grams of oxygen? So let's walk through this one again real quick. We have, how do I set this up? How should I start?
8.0 grams of oxygen.
So yeah, 8.0 grams of oxygen. And then Taylor, you said the molar mass, use the molar mass. How are we going to use the molar mass of oxygen?
The molar mass of oxygen should cancel out. Well, not cancel, but
Convert to moles of oxygen. All right. So did he use? That's a mean question, Mr. Hobbs. That's a mean question. So what he meant by 20, and I think this is something that he messed up on, or not messed up on, but just forgot to mention for y'all. I think when he said oxygen, he meant oxygen gas. And so oxygen gas is always diatomic, which means it exists as O2, right? So the molar mass of oxygen is 16, right? But if it's the diatomic gas, which is how it exists normally in nature, what are we actually dealing with? 32, right? Because it's 2 oxygens. So he didn't mention that on the problem, but usually if we're talking about oxygen that exists in real life, we're talking about O2. And so try to remember that, especially with like a lot of the gases that could exist in nature, so like nitrogen or chlorine, for example. Be adamant to try to make sure, if that's not on the test, to ask, are we talking about chlorine gas or are we talking about just the element itself, chlorine? Because it's a little tricky there, and I don't know why it wasn't mentioned in the problem. But that's just an important distinction. So 32.00 grams per mole of oxygen. Okay, so next we need to convert. What do we need to do next? So we're trying to get to grams of silver in the same number of particles that are in 8.0 grams of oxygen. Or sorry, not grams of silver, grams of sulfur.
So change 1 mole to 1 mole of sulfur.
So convert, yeah, you can convert directly to moles. Yeah. We know that 1 mole of O2, again, there's a difference between molecules and particles, or atoms, right? But at the end of the day, they're both 6.02 times 10 to the 23rd. So we can still directly convert, even though it's a little weird. We can still directly convert because a mole is always going to be a mole.
Wouldn't oxygen go on the bottom to cancel out the...
Yes, it would. I got carried away. Absolutely right. Yeah, 1 mole of sulfur on the top, 1 mole of oxygen on the bottom, so we can cancel out the oxygen. Right? And then finally, what do we do from here?
Convert to grams.
Convert to grams using not atomic mass, but molar mass of sulfur. Right? So in the book, or in his guide here, that just so gracefully turned off on the computer, we use 32.07. Again, you'll have these numbers on the test. So don't fret about it too much. You don't have a periodic table to use. And even if, yeah. So here we go, 32.07 grams per mole. All right, and again, sulfur, sulfur. So if we cancel all of these out, canceling like this, basically what you're doing is 8.0 divided by 32.00 times 32.07. So if y'all want to quickly do the math for that, actually, how much time do we have? We don't have much time. I'm just going to tell you. Because we don't have much time, I want to get through the rest of the problems. 8.02 grams of sulfur. So I'll let you do the third problem on your own there. So if you want to go back, if you're trying to study, try to do the third one on your own. I'll post this video as soon as I can. So just keep that in mind on how to convert to kVs. So now we're just talking about our 24 here. So this is the element table. I'm just going to do one of the element tables and we'll go from there. So we'll take the third one with AS. I don't remember. I think it's arsenic. Yeah. I can't remember. I can't memorize the entire periodic table. I'm not that good, unfortunately. I know back in the day, some people would make you, which is miserable in my opinion. But okay, this is number 24 here. So number of protons. What do we think?
33.
33 protons. So why is it 33?
Because that's the atomic number.
Because that's the atomic number, and we got that from the periodic table, right? So,
I don't think there's a 2 minus.
There's no 2 minus.
in the answer sheet there is. That's oh, that's because we're filling it in. I've spoiled it.
You're supposed to. Oh.
Okay. So I spoiled it. That's what happened. So we're doing. That's my fault. Let's do this other one instead. Okay. So the second one. We'll do the second one. Number of protons are given. What else were we given? Atomic number, mass number. I know those are at the front, but I'm just going to write it here because I did it earlier. Running out of time. There we go. Okay. So in this one you were given the atomic number, you were given the mass number, and you were given the number of electrons. Okay, so the number of protons, what is it?
Should be 10.
Number of protons?
Oh, protons.
Protons, 8. Why is it 8?
Because the atomic number is 8.
Atomic number is 8.
Neutrons is 10.
Neutrons,
10.
10, right? Why is it 10?
Because 10 plus 8 is 18.
10 plus 8 is 18, and now it's one more mass number, right?
Yes.
So the symbol we're going to write out. First off, what element do we think this is?
Oxygen.
Oxygen. All right. What is the mass number of oxygen?
8.
Put it up here. Mass number or atomic number?
Oh, atomic
Oh,
number.
atomic number.
Mass number is mass.
18.
Talking about mass number right now. What is mass number?
The atomic number is 8.
Mass number is 18.
Mass number is 18. That's what I was asking for. I heard 8 and I was like, let's talk about mass number. Yeah, not bad. I should have made that a little more clear. What's the charge in this?
2 minus. 3 minus. No.
I hear 2 minus and I hear a 3 minus.
2 minus because there's 2 more electrons
Yep.
than protons.
2 more electrons than protons, right? So that's your justification for 2 minus.
Did I miss?
You-
I probably did.
I probably mistyped it.
2 minus for arsenic.
Yeah. That's essentially the same thing you want to do for the rest of that table. Does that make sense? Alright, and so I don't think I have enough time to cover really much of 25. But we kind of covered a lot of the concepts of 25 with number 20 when we converted there. Yeah.
So, like, for the Avogadro's number, when do we use that for conversion?
If we have moles and we need particles, right? Because again, Avogadro's number is 6.02 times 10 to the 23rd particles per mole. So again, that could be number of atoms, could be number of molecules, could be number of donuts, doesn't matter. All right? If you have a mole of donuts, you get 6.02 times 10 to the 23rd particles per mole. Same thing with atoms, same thing with molecules. Does that make sense? All right. Yeah, I'm sorry we didn't get to that last problem, but hopefully, I would try on your own in the book. It's page 93, 17 through 19. Those would be pretty good review problems for you. So if you haven't already done those. And those will kind of cover converting between, doing your conversions as well as average atomic mass, which is number 19, calculating that.
So the test tomorrow will go live at the same time. Right?
Yeah, it'll be tomorrow. We'll be going live at some time.
Can I eat in here?
Hello. Y'all have a test today. Are you excited for a solution test? I mean, it's solutions. There's nothing more fun in chemistry than solutions. I mean, to be good, but solutions make up a lot of chemistry. We'll be doing them all the time. Talk about just the class is so hard.
The last test. Like I'm usually like last year chemistry was so easy. And like the stuff we do here is mostly